Hello, my name is Carla Pinto. I'm an adjunct professor of the School of Engineering of the Polytechnic of Porto in Portugal. I'm going to talk about the effect of different control strategies on a non-integer order dengue model. This is a joint work with Professor Dumitru Baliano and Professor Amin Jarjarmi. And the main focus is to access the effect of 4 different control strategies in dengue progression, namely the existence of sterile male mosquitoes, the use of pesticides, both for aquatic phase and adult mosquitoes, and vaccination. We'll discuss the results from an epidemiological point of view, and we'll state the main conclusions, and there will be time for a few questions. So dengue is a mosquito-borne viral infection. It is caused by the dengue virus of the Flaviviridae family. And we can distinguish 4 serotypes, DV1, 2, 3, and 4, which means that someone may have dengue for at least 4 times. So being infected with one serotype does not provide immunity for an infection by another serotype. And so how is this infection cycle? We have a mosquito, which is a wild mosquito. He bites a person that is infected. Then this mosquito spreads the disease to a non-infected person, a non-infected human by a bite. And then this human being, from 4 to 13 days later of incubation period, he gets again the disease. And so this goes on and on. And there are 3 transmission modes: mosquito to human, human to mosquito, and mother to child, vertical transmission. So when a woman is pregnant, she can infect her child with dengue. So the infection by dengue may be very smooth. So the subclinical disease, like a very mild flu, or develop to severe dengue, and this one is hemorrhagic, and people die from hemorrhages. And so we propose a new model for dengue infection, where we consider the aquatic phase of mosquitoes, and then we divide the female mosquito, which is the one who spreads the disease, in 4 different states. F1 is uninfected and unmated female mosquito. F2, uninfected fertilized female mosquito. F3, uninfected mated fertilized female. And F4 is the infected mating fertilized female. And we also consider 2 species or subtypes for the mosquitoes. We consider the normal male mosquito, and then we spread in the environment the sterile male mosquitoes. The human population is divided in 4 subpopulations: the susceptible human, the exposed, the infectious, and the recovered. These are the variables of our model. As to the parameters, we have the aquatic mosquito recruitment rate, the carrying capacity of aquatic and adult mosquito. We have the mosquitoes transition rate from aquatic to adult stages. We have the mosquitoes aquatic form mortality rate. We have the proportion of female mosquitoes. We have the mosquitoes mating rate, and we have the mosquitoes natural death rates. Then we have the contact rate female mosquitoes to humans. We have the average bite per mosquito per day, the alternative non-human blood sources, the recruitment rate for sterile male mosquitoes, the human natural death rate, the transmission rate from humans to mosquitoes, the partial immunity, and the incubation rate of the mosquito, and the recovery rate. And so these are the equations of the mosquito population. We have here the aquatic phase. The mosquitoes are, the larvae are, come from the female mosquitoes, and they move to a female stage with this at this rate, and they die at this rate. These are the uninfected female mosquitoes and then mated. And so as you can see here, we have the variation of the dynamics of the 4 different types of females and 2 different types of male mosquitoes, and they obey to these rules. This parameter over here is just a modification parameter, very close to 1, just to keep the right units of the model. And so these are the equations for the human population, from the susceptible humans exposed infectious to the recovered ones. And so the humans are beaten by the F4 female mosquitoes, which are adult, mated, and infected female mosquitoes. And so we have performed numerical simulations for the effect of male sterile mosquitoes for different values of the order of the fractional derivative. You can see here that with and without control, there are changes in the dynamics. As you can see, for example, here, it's the female uninfected mosquitoes. Without control, they are higher number than with control. And so, as you can see here, also the infected adult female mosquitoes with control. So, when you sterilize, when you spread sterilized male mosquitoes, they mate also with these females mosquitoes, and then they don't mate with other mosquitoes, and so there are less infected female mosquitoes to bite the susceptible humans. And as you can see, the susceptible humans, the number is bigger when you have these spreading of the sterile male mosquitoes in the environment. Also, you have an increased number of infectious humans when you don't have any control. There is when you don't spread the sterile mosquitoes, male mosquitoes. This is a similar behavior for a value of the order of the fractional derivative equal to 1, which means we have the integral order model and we have a similar behavior, only the values are different here in the y-axis. It's because of the memory effect. On alpha is equal to 1, there's no memory effect. And the numerical simulations with respect to effect of vaccination when alpha is equal to 0.7. You can see it here that we have, for instance, the number of susceptibles is higher when there is no vaccination, of course, because when they are vaccinated, they are considered recovered, since they are so immune to the disease. And so you have less controlled, less susceptible humans also. When you have vaccinations, since if you are vaccinated, then you're not susceptible to the disease. And also, since we have a lower number of humans, then the infected female adults are also less, because there are no infected humans to infect the mosquitoes, and so they mate with uninfected mosquitoes, so they do not become infected too. And so you can see a similar behavior here for alpha equal to 1.0. And so vaccination is a good control strategy in this case. Also, we have performed the numerical simulations to assess the effect of aquatic pesticides. So pesticide in the larvae stage. And as you can see, there's a reduction of the larvae, of course. and this also translates in a difference in the amount of adult females which are infected. They have already mated, and with control. So if you have less larvae, you have less infected adult females. Also, if you have less larvae, less adult infected females, and then you have more people susceptible, of course, because they are not bitten. This same thing, the same type of behavior happens when for the aquatic pesticide, when alpha is equal to 1, there is the integral order model. Eva also provided numerical simulations for the pesticide for adult mosquitoes. As you can see, there's a significant reduction in the number of adult female infected mosquitoes. So when you use pesticides, that means also that the number of mosquitoes infected is significantly reduced. And also the number of humans who are susceptible is higher than, of course, if you don't have any control, if you don't kill the mosquitoes. So we've done this, we repeated the simulations for alpha equal to 1, and we observed the same behavior. And so we have accessed the 4 control strategies: use of the pesticides in the mosquitoes aquatic phase, and use of pesticides in adult phase, vaccination, and release of sterilized male mosquitoes in the dynamics of dengue infection in a fractional order model. We observed biological reasonable results for the values of for all values of the order of the fractional derivative. So we use real data to compare results and find the best fit as a function of the order of the fractional derivative. And I leave here one question: what is exactly the role of the order of the fractional derivative here in this model or in any other model? I also invite you to attend the International Conference on Mathematical Analysis and Applications in Science and Engineering in next June 2021. We hope you have already a vaccine, if very safe vaccine for against SARS-CoV-2. And these are some references, and thanks. And if you have, please, questions or remarks, please, you can share them with me. Thank you very much. Bye-bye.